Welcome to our Saturday Physics for Everyone lecture series. So today is actually a special occasion because this afternoon we'll be launching the very first public quantum network. That's basically going to be a quantum link between this physics building and the Urbana Free Library. And so you might ask, what exactly is a quantum network? Hopefully we'll get the answer this morning. So it's my great pleasure to introduce today's speaker, Professor Elizabeth Goldschmidt. She's a rising star in our physics department. Professor Goldschmidt obtained her bachelor's degree in physics from Harvard University in 2006, then did her PhD work at the University of Maryland at the JQI, the Joint Quantum Institute, and received her PhD in 2014. She then went to NIST, or the National Institute of Standards and Technology, where she did postdoctoral work there, and then was a staff scientist at the US Army Research Lab. So her expertise is in quantum optics and quantum information, and she's going to tell us about how quantum physics and all the kind of weird phenomena that come out of quantum physics is going to revolutionize things like computing, information security, and the next generation of sensors for the next decades or so. So let's give a nice welcome to Elizabeth. And, we look forward to her talk. And she said you can interrupt if you have any questions, but we'll have plenty of time at the end for questions from the audience.
Yes. Thanks, Jan. Is this on? Can people hear me? Great. Thanks, Jan, for the introduction. Yes, please interrupt with questions throughout. I am happy to take them. And it's always a little hard when we go about explaining science, especially to people with mixed backgrounds, to kind of guess ahead of time what people know and what they don't know. And so if there's something that you don't understand, I'm sorry, that's my fault, not your fault. And there are probably a bunch of other people who also don't understand it. So please feel free to ask questions. So yes, I'm going to talk today about quantum networking with light, with photons. So photons are like particles of light. And in fact, photons, or light, is what we use to communicate quantum systems. And we're going to talk about why that's the case today. So the basic outline for today is going to talk a little bit about why we might want to build quantum networks, why our regular classical networks, so I'm going to use the word classical to mean not quantum, why our regular classical networks don't fulfill all of the needs, all of the things that we want. And then I'm going to spend a lot of time talking about what makes quantum things different from classical things, what actually makes something quantum mechanical, and what is so weird about that. And then I'll end by talking about how we actually do experiments or measurements of quantum systems to show this weird, uniquely quantum behavior. And then the last thing I'll probably show is a little bit of data from the entangled photon source that's going to be used this afternoon to distribute quantum entanglement between here and the library. And so I do encourage you all to come this afternoon. I'm going to pop up some information about it. Later, I'll be there too, so if you don't get to ask your question now, if you come to the Urbana Free Library this afternoon, I will be there to answer questions as well. Okay, so I want to start with a little bit of terminology for today, right? The kind of words that I'm going to use today that I decided I couldn't get away with not using, so I wanted to define them first before I got too far into it. First, a qubit, or a quantum bit, right? This is some quantum particle that can encode not a regular classical bit of information, but what we call a quantum bit of information. We're going to talk a lot about what that means. But that's what a qubit is. It's a quantum bit. And we're really going to think about it as some like physical thing. And we're going to represent it as this little spinning ball, right, with an arrow. Okay. Entanglement. Quantum entanglement. This is a uniquely quantum property that can be exhibited by two or more quantum bits or other quantum systems, right? We're going to talk a lot about what this means, but for today, little glowing lines looped around two things is going to denote that those two things are quantum entangled, right? And then finally, you might think you know the definition of the word measurement, but I'm going to hope to try and get you to think a little bit more deeply about what it actually means to measure something. And then, because then we're going to talk about what it means to measure a quantum something, which it turns out is different. So really, the real definition of measurement is I do something, some physical action, or something does some physical action onto some system, and information comes out. That's what a measurement is, right? A measurement is some physical action that produces some information. We're going to talk about what that means, but right, I could measure the width of this countertop, and I would produce information, which is the length of this countertop. But it would require me to do some physical action, either take a tape measure and do this, or some other way measure that distance, right? Even if the physical action is looking at something, that requires light to bounce off the thing and into my eye. If I turned all the lights off, I wouldn't be able to make that measurement. The physical action in that case is illuminating the system with light. Okay, those are our definitions for today. So before we talk about quantum networks, we should probably define classical networks, right? So a classical network is something that can do a lot of things. It can enable communication between two or more parties, right? It can connect people together to form a cloud or some kind of distributed computing system, and then give people access to that cloud or distributed computing system. And it also can enable much more powerful sensing, and we're going to talk about that in a second, than individual sensors. So the network you probably are all thinking of is the internet, right? That's maybe the most common network that we have, but networks have been around a lot longer than that, right? This is a network, right? A bunch of people calling a switchboard and changing and making, somebody sitting there and making those connections. That's a network, right? And in fact, one of the most important networks that you maybe don't think about quite as much is GPS. So this is a case where networking together classical things, which in this case are clocks. Every GPS satellite is basically just a clock that can communicate. Networking together clocks, allowing them to communicate with each other and with anyone on the ground, is what allows us to locate people, or allows you to locate yourself, or allows anyone to locate themselves by connecting to this network. This is what I mean by sensing. Sensing means discovering my position, for instance, right? That's sensing. And I can do it much better with this network of satellites than I could possibly do without that network, with just some local something that could try and figure out where I am, right? Okay. So what's a quantum network? Yeah, Jan, did you have a question? No. So what's a quantum network? Okay, so what a quantum network is I've just replaced all of my connections with my little entanglement links, right? That's what the glowing things connecting the little spinning balls mean. So a quantum network is some set of people or nodes or whatever, however you want computers, right, that share quantum entanglement, right? And what can quantum networks do? Well, we said classical networks enable communication between two or more parties. Quantum networks enable secure communication between two or more parties, and we're going to talk about why that's the case. Classical networks enable cloud computing. Well, quantum networks allow connections to quantum computers. I am not going to go into detail about quantum computers because that's a whole other Saturday Physics for Everyone talk that hopefully someone has or given or will give at some point, and I do encourage you to learn more about it, but I don't have time to talk very much about it. Just to say that quantum computers would enable much more powerful computing in certain circumstances, but they are very, very hard to build, and they will remain very, very hard to build for a long time. They're not something, I think I'm safe in saying this, they're not something that you're going to put in your pocket really any time in the future. They're going to be these, right now they're basically big physics experiments. And they're going to stay big physics experiments for a long time. Even once they become useful, they have not yet become useful. And in that point, you're going to need to be able to connect to a quantum computer in order to use it. The quantum computer is going to be housed at IBM or at the National Institute of Standards and Technology or somewhere else, and for anyone to use it, you're going to need a quantum network to be able to connect to it so that you can make use of these very rare and hard to build and maintain quantum computers. Right? And networking them together is going to make them more powerful, just like networking our classical computers together makes our classical computers more powerful. And then finally, a quantum network enables even more powerful sensing than a classical network. If I were able to entangle my GPS satellites with each other, if I were to get my GPS satellites to share entanglement with each other, the ability with which I could pinpoint a point on Earth would go through the roof, right? Instead of getting some few kind of meters worth of resolution, I could probably get to some very, very, very tiny resolution like that, right? So I really do encourage you, if you want to learn more about quantum networks, please come this afternoon to the Urbana Free Library. The event starts at 1 o'clock. There's going to be a whole bunch of presentations. There's going to be a bunch of information there and hands-on activities about quantum information, quantum networking, and there's actually going to be a permanent display at the library going forward, if you can't come this afternoon, that you can check out on your own time. Right, so it's going to be a lot of fun this afternoon. Okay. Oh, and I should say the thing that's actually happening this afternoon is we're making one of these links, where Loomis Laboratory of Physics is one end, the library is the other. We're going to distribute entanglement between the two places. Okay, great. So, what makes quantum physics different from classical physics? Or what makes quantum information different from classical information? The first major difference is this shift from bits to qubits, from bits to quantum bits. A bit, which I've drawn here schematically as just a transistor, right? A bit is some physical thing that has two possible configurations, like a transistor that can have high or low voltage, right? And we label those two things 0 and 1. And it's either 0 or 1, right? And in fact, today, we no longer worry about, well, most of us, the people who are trying to build better and better computers, most of us don't worry too much about what the actual physical thing is that our bits are made out of. We just abstract that away. We think of them as a logical thing, a logical 0 or 1, right? Yeah. But in quantum information systems, where we have quantum bits, we're still very much in the nascent stages. We still do have to think a lot about even what the physical thing is that's going to be our qubit, right? And the big difference between a bit and a qubit is that unlike a bit, which can only be 0 or 1, a qubit can be in what we call a superposition state. So we're going to talk about this for a minute now, right? So a qubit can have some character of 0 and some character of 1, right? The way that we represent a qubit, the way we represent a bit is we either write 0 or 1. The way we represent a qubit, we actually use a sphere. We use a whole sphere and we label the poles 0 and 1, and then all of the possible states of the qubit are all of the points on the surface of the sphere. This is the kind of the most compact way to describe a quantum bit. This is super weird. This shouldn't seem obvious to you, right? This is very, very strange. This is why this is the first major difference in my talk, at least, between classical and quantum information systems, right? This is also why I use a little spinning ball as my qubit, because that, you can imagine that arrow pointing in any direction, right? So we can describe these things with like a latitude and a longitude, effectively, right? Because it's like the surface of a sphere like the Earth, right? And this superposition has to do with, okay, how close to 0 am I pointing versus how close to 1 am I pointing? That's kind of like how much like 0 am I versus how much like 1 am I, right? But the next weird thing about this, there's going to be a lot of weird things, right? The next weird thing about this is when I go to measure my quantum bit, just like when I go to measure my bit, there are only two possible answers. When I measure my bit, I can either get 0 or 1. When I measure my quantum bit, similarly, there are going to be two possible answers, right? That's weird because there are an infinite number of possible states, but there are only going to be two possible answers when I measure. This is now what we're going to talk about. How's everybody doing? Great. Before we talk about quantum measurement, let's talk about classical measurement, right? A lot of things that we measure are these kind of deterministic measurements. I take a ruler, I measure the size of this thing. Or I ask my computer what's the value of this bit, and it tells me either 0 or 1. And every measurement that anyone has ever made or will ever make in the universe has some uncertainty associated with it, or some precision associated with it, and that's true. But these deterministic measurements, that precision or that uncertainty, that is just set by how you're making the measurement. How fine the ticks are on your ruler, how good the electronics are in your computer, whatever. There's some precision, but you only got to make the measurement once, right? And you get the answer. But not everything is like this, right? There are also a lot of things where in order to get the answer, you actually need to make many measurements. You cannot get the answer out from one measurement. If I wanted to know how fair this coin was, I would have to sit here and flip it a bunch of times. All right, tails. Does that mean it's going to come up tails every time? Can I make that assumption? No, of course not. Everybody knows that of course I can't, right? Things like polling and randomized trials are also like this. If I want to know if some new medical treatment works, I can't try it on one person, see that it either works or doesn't work, and declare that it either works or doesn't work. Right? That's not how this works. Right? This is statistical noise. Right? These are probabilistic measurements. These are things where I fundamentally can't learn the thing by just making a single measurement. Right? And to hammer that home, right, we can even simulate or calculate how well we know a thing based on how many measurements we make, right? If I were to flip this coin, this is just a simulation. I didn't actually flip a coin 1,000 times. But I can simulate it on a computer real fast, right? If I were to flip this coin a whole bunch of times and write down heads, tails, you know, whatever it is, and then plot the average that I've seen so far, the average fraction that are heads that I've seen so far, right? It would converge to some number. It would converge to some number, which here I've drawn as 50% for a fair coin, after enough measurements, right? If I make too few, I've done a bad measurement. There's too much noise. Eventually, this uncertainty drops, the precision increases, right? And I can understand this much better, right? So just for fun, because we have the demo, right? If I come over here to my Plinko board, right? If I start dropping ball bearings in here, how do you think they should fill the slots at the bottom? Yeah? You were going to say the right answer. I could tell from your hand motion. Like a bell curve. Right, exactly, because I'm dropping them all in the middle, so they should fill it like a bell curve. But if I only drop a few, does that look like a bell curve? No, right? But if I poured, I'm not going to because it'd be very loud, but if I poured all of these in here, right, eventually I would form a bell curve, right? And I would get this same effect. This is going to be very important because it turns out quantum measurements have this same statistical property. That's why I'm kind of hammering this home, right? So this kind of uncertainty or noise, it's not because I'm bad at making the measurement, right? The reason I can't tell if this is going to be what the probability of heads from this coin is isn't because I'm bad at flipping the coin, right? It isn't. There's nothing I could do to change that. I have to make many, many measurements. I have to get the data out of the statistics. I cannot get it out of a single measurement. And it's not my fault. It's nature's fault. Okay. Whew. So far, so good. So let's put this together. So we said that the possible states of our qubit live on the surface of this sphere, right? The possible states of the fairness of this coin live on some line, right? It could be that it comes up tails all the time. It could be that it comes up heads all the time, right? The actual real value of the fairness of the coin is some point somewhere on this line, right? And analogously to the state of my qubit is some point somewhere on this sphere, right? So I said, though, when I make a measurement of my qubit, I only have two possible outcomes, right? And in fact, not only that, when I make a measurement of the qubit, I actually have to choose what measurement I make. And that choice can be represented by a line that goes through the middle of the sphere. So if I take a sphere, or the Earth, and I draw a line through the middle of it, I'm going to get 2 points on either sides of the sphere. Every measurement that I make of my qubit can be represented by some line that goes through the center, comes out at 2 points. I'm defining what the two possible outcomes are. It's not like a coin. When I flip a coin, right, I can get heads or tails. My coin can't come up blue, right? I can't get something other than heads or tails. This is a big difference between bits and quantum bits. When I measure my transistor, high voltage, low voltage, not purple. I don't know. It doesn't even make sense to talk about, right? But in a quantum bit, I get to decide what the two possible outcomes are. And the way that I represent this is this kind of a line. But the line doesn't have to go through 0 and 1 like I've drawn it there. It can go through kind of any pair of points that I can then go and label 0 and 1 if I want, but I have to also give you the information about what the measurement is that I made, right? The measurement is defined with the whole thing. It doesn't matter. Any of these are fine options. And the probability now of which one it lands on, what the outcome of my measurement is, it has to do with how far away my true state is from the two possible outcomes, right? And this means, like a coin, I can't determine its state with a single measurement, just like I can't determine the state of the coin with a single measurement. But here, I can't even determine the state of the thing by making the same measurement over and over again, right? If the true state of my bit was on the equator, and I measured in the up-down direction, right? Half the time I'd see up, half the time I'd see down. I would know my true state was on the equator, but I wouldn't know where on the equator it was. I have to make usually 3 measurements, because there are 3 dimensions, to actually locate where on that sphere my qubit is. And I have to make each of those measurements many, many, many times, because everything is statistical, right? So measuring the full state of a quantum bit is even harder than measuring the fairness of a coin, which is even harder than measuring a bit. Because measuring a bit, I get to just measure once. Right. Okay, that's not it, though it keeps getting weirder. Right? In addition, when I make my measurement, my quantum particle collapses or changes its state to the thing that it was measured. Right? So it goes from whatever it was to now whichever outcome it is, which is probabilistic. So sometimes it'll fall down there, sometimes it'll fall down here. The way I had drawn it, I think it'll fall more in the direction that I drew it than in the other direction. Now, this is actually not that weird when I flip my coin. Okay, I got tails. It's still tails, right? I've made the measurement, it's tails. I got to reset it and flip it again to try and make another measurement. So that's not maybe so crazy. It's a little crazy, but it's maybe not so crazy, right? But it does have some weird kind of effects that are counterintuitive. So we're going to use today here and also this afternoon at the library the polarization state of photons, particles of light, as our qubits. So our qubits are going to be the polarization of light. So who here has worn polarized sunglasses and tried to look at a screen and seen that the brightness of the screen is different when you rotate it compared to your sunglasses, right? Maybe, maybe not, right? Because what a polarizer is it's basically a measurement of the polarization of the photon, or a measurement of the polarization of light, right? I have a polarizer here. You probably can't see, but there are arrows pointing up and down. That means my polarizer is aligned like this. So light, whose polarization, which is a property of light like color, if its polarization is pointing this way, it'll go through. If the polarization is pointed this way, it won't go through, it'll be rejected. And if it's anywhere in between, it'll probabilistically go through or get rejected depending on how close it is to vertical and horizontal, right? But it also is what we call a projective measurement. Once the light goes through the polarizer, its polarization is the thing that the polarizer said it was. So the light coming in right now to here is polarized in every direction. But the light after is all polarized vertically. Okay, that's fine. So about half the light's getting through. That's normal. And the light is now all going to be polarized this way. So if I take another polarizer and I align it the other way, so now they're crossed, no light will get through. Right? I can do it like this, so you can see half the light getting through on the top, but here on the bottom there's just no light possibly getting through. Right? But what this means is that the light between the two polarizers is perfectly polarized in this direction. So if I took a third polarizer and I put it in at an angle with respect to the other two, only some of the light's going to make it through, but it'll change its polarization. And then when it goes through the third one, it'll no longer be perfectly perpendicular, and some of it will get through. So even though the only thing a polarizer can ever do is reduce the amount of light going through it, by adding a third one, I get light suddenly coming through where there was none before. This is weird. This, right? This is pretty strange, right? This is the weird part about quantum measurements changing things, right? Or this is one way to understand the weird part about quantum measurements changing things. Every time my light goes through a polarizer, not only am I making a measurement of the polarization by determining whether that photon went through or got rejected, I'm also changing it, right? And I'm changing it in a way that's perfectly measurable, because I can do this demo and see with just 3, cheap polarizers I can buy anywhere. I can see that it actually is true, that my measurement is changing my thing, right? This is cool. How's everybody doing? Yeah. I am changing the light, right? So I'll even do it like this, right? My polarizers are crossed. So the light coming up to here is polarized like this. This polarizer is polarized like this. So no light is getting through. It's all getting rejected. So this polarizer is acting as a measurement, and the outcome of the measurement is rejected. We could label transmitted and rejected as 1 and 0, but the outcome is rejected, right? If I put this guy in between at some angle, right? This guy's also making a measurement, right? And it's sometimes rejecting and sometimes transmitting, but it's also changing. And that means that this measurement, which was always here and didn't move, I'm now getting a different outcome on this measurement than I was before. Mm-hmm. Yeah? Unfortunately, it's not. Yeah. So polarization is a thing that can point in any of 3 dimensions, right? But each particle is just one particle, just like the coin flipping, right? So this, with photons, if these were individual photons, right? Each particle is one particle. Each particle either goes through or gets rejected, right? That's why it's the statistical thing. Each coin flip is either heads or tails, right? And so this is why when I have one photon at a time, which is not what I have with my handy-dandy overhead projector, but it is what I will have this afternoon at the Urbana Free Library, the way I want to think about this measurement is for every photon, it's either going through or getting rejected. Good question, thank you. All right. I can turn this off, in fact, so I don't burn my polarizers. Okay. This is going to get even weirder. Because the thing that we're going to prove today is that the outcome of these quantum measurements actually doesn't exist until I make the measurement, right? When I flip my coin, as soon as the coin leaves my finger, if I knew exactly the weight distribution of the coin, exactly how I had flipped it, every air current in the room, I could tell you, I can't know this, but I could tell you, depending on where I grabbed it, whether it would be heads or tails, right? And so if I grabbed it up here, I could still tell you what it would have been if I had grabbed it down here, right? Normally, when we think about measurement, if I measure the size of this table, it's not like by measuring it, I'm making it have a size. It has a size. I might not know it. I measure it, and then I know it, right? We usually think of measurement as the discovery of information that exists, right? It turns out quantum measurement is not the discovery of information that exists. It is the creation of new information. This should also sound insane, right? Many people thought this was insane, in fact. What I want to go through, mostly I think with the rest of my time, is the fact that people finally figured out how to tell the difference between whether quantum measurement was learning something that exists or creating new information that didn't exist until I made the measurement. And surprisingly, quantum mechanics won that, which I think a lot of people were surprised by when this happened, and won the Nobel Prize last year. Okay, let's keep going. So a really quick aside, because this is something that gets a lot of people confused. Quantum measurement does not require a person or a sentient being intentionally making a measurement, right? There is no requirement that someone is looking, right? Anything can measure anything. Any interaction of the qubit that I care about with anything else in the environment, any other atom or molecule or photon or whatever, can measure it, right? So we're going to talk about me making measurements. In order for me to make good measurements, I have to make sure that nothing else is measuring the things that I want. So most of quantum science is figuring out how to make sure my quantum systems don't interact with anything else and only interact with me, right? For the experts in the audience, in fact, what happens is the quantum system that I care about interacts with some quantum system that I can't control and can't measure and don't care about, like some other atom that flew by and is long gone. They become entangled through that interaction, and when I go and measure my quantum system, it looks different. It's been changed. But that's just because I can't measure the other one, right? This is what we call decoherence. If you've ever heard about the coherence time of a qubit or the coherence time of your quantum computer or whatever coherence you've heard about, this is it, right? It's that things become entangled with things that I can't measure, and it appears like their state has been changed, right? When in fact their state has simply been expanded. And this is really why it's hard to build quantum computers, right? Because somehow I need to take some quantum system, and I need to be able to get in there and control it, and I need to have a bunch of qubits that I can force to be entangled when I want them to be, and that I can prepare and that I can measure, but that don't interact with anything else, because nothing else can possibly be measuring them or becoming entangled with them. And these two things are opposite needs, right? It's very hard to make a system that is both isolated and connected, right? And that's why you don't have a quantum computer in your pocket. Okay, that was my quick aside. So the last thing before we get to entanglement and measuring entanglement is just to point out another weird thing about quantum systems, which is I can't copy them, which sounds weird. Like, of course I can copy them, right? If I send you a string of bits, you just say, okay, that's the string of bits. I look at it, I measure it. You can make as many of those strings as you want, and either send them all to your friend so that if some of them get lost, your friend will still have the string, or you can send them to many of your friends, to as many people as you want, right? You can store them in memory. You can do all of the things that you would want to do with information, right? But let's go back to that quantum measurement, right? If Alice sends Bob a qubit, it's always Alice and Bob, and then Charlie if we need a third person. If Alice sends Bob a qubit, Bob has to make a choice when he measures it. And depending on the choice that he makes, he's obviously going to see one of the two things that he's chosen, right, with some probability, depending on the choice that he makes. If he happens to choose something where the true state of the qubit is along his choice, he'll always see the same thing. But if Alice only sends him one qubit, he has no idea what the actual original state was, right? The only thing he learns from his measurement is that if he measures up, that the qubit wasn't identically down when it came to him. He has eliminated one point on the sphere, and it could still be any other point on the sphere with some set of probabilities, right? So if I send you one qubit in an unknown state, or one string of qubits in an unknown state, in a set of unknown states, you cannot make a copy of them. You cannot store them in memory. You cannot amplify the signal if it's running over a lossy channel, which is actually a huge problem, right? All you can do if you want is make a probabilistic measurement, but that measurement is never complete. You can never make a complete measurement of a quantum state with just one measurement, right? And you change it when you measure it, right? So this fact that you can't copy or amplify a quantum state is another reason we don't have quantum computers, because your computer has redundancy, right? It stores your bit not just in one atom. That would be a very silly way to build a memory inside of your computer, is that if every bit was stored in a single atom, because if that atom, something happens to it, then you've lost that bit of information. It doesn't do that. That would be silly, right? It copies things. It builds in redundancy. Can't do that. You can't put redundancy in a quantum computer. It's really hard. Okay. Any questions now? Good. So finally, we'll get to entanglement, which, as weird as it's been so far, gets weirder. So an entangled state of qubits is a joint state where measuring one changes the other. That's weird. And the outcomes of your measurements of the two things are correlated in ways that no theory of classical physics allows. So let's explain what that means. The words are maybe not that helpful, but let's use some pictures. If I have two qubits that are not entangled, and let's say I prepare them both pointing right, and I send one to Alice and one to Bob, and Alice and Bob each measure in the up-down direction, they'll each get a random string of bits. Half the time they'll measure up, half the time they'll measure down. They will be different random strings of bits. Nothing is going to make those random strings of bits the same or anything, right? This is relatively normal. If instead I start with an entangled state, and this is my representation of an entangled state, right? My entangled state here is that I am in a superposition of either both qubits up or both qubits down, right? This is one of the most popular entangled states. This is an entangled state, right? Now, when I send my qubits to Alice and Bob, it is still the case that each one of them will measure up half the time and down half the time. However, they will always measure the same thing. That's not that weird, right? If Charlie, I said a lot of things are weird. This is actually not that weird. If Charlie was sitting in the middle, just randomly deciding to send two ups or two downs, you'd get the same thing, right? this is not weird. This is not the weird part. Right? I can do this classically, just by, having a person in the middle. Alice and Bob don't know that they had an entangled state just by making this measurement, because this could be done totally normally and classically. First weird thing, doesn't matter which direction Alice and Bob measure, they'll still get the perfect correlations. So even if they both measure left-right, they'll still get the same thing every time. And that wouldn't be true if Charlie was sitting in the middle, choosing randomly to send 2 ups or 2 downs, right? Because if Charlie was randomly choosing 2 ups or 2 downs, sending them to Alice and Bob, and they measure in the left-right, each one's just going to get a random number each time, but those random numbers have nothing to do with each other. But for an entangled state, they'll still be perfectly correlated. Right? That's weird. Right? I want to say something here, because this is another thing that lots of people get wrong. So if you take 2 things away from my talk, quantum measurement doesn't require a human or a sentient being, right? And 2, yes, it is true that instantaneously when Alice measures her qubit, she knows the value of Bob's qubit in the same basis, or in the same direction of measurement, right? Instantaneously, even if they're on opposite sides of the world, faster than they could communicate. This does not let them communicate faster than the speed of light. You cannot communicate faster than the speed of light. If someone tells you you can communicate faster than the speed of light, that person has misunderstood something. Because Alice can't actually send a bit of information to Bob. She simply learns instantaneously what random bit he has. That is different than communicating. Yeah?
She measures at a certain period of time. They're both measuring, or the outcome is the same. He measures at a different period of time. Will that outcome be different?
Nope. Whoever measures first collapses the state. Right? So as soon as Alice measures, if Alice measures first, if she sees up, no matter when if Bob already measured, we know that he already saw up. If he's going to measure, we know that he will see up. Right? Even at timescales faster than the speed of light. This is very subtle, though. You cannot design a way to use this to actually send information. You could try, but you'll fail. Right? You cannot use this mechanism to intentionally send any information between Alice and Bob. If you read the popular news media about quantum entanglement, the number of times they claim that it lets you communicate faster than the speed of light is very frustrating, because it's like the only rule. Okay, sorry, that was my rant. Thank you for listening. Okay. The actual crazy things of this, though, in addition to the instantaneously, it's weird. It's super weird that Alice knows instantaneously what value Bob would get. It just doesn't allow superluminal communication, but it's very, very weird. The other weird thing is that we're going to prove, I've got till 11:30, 11:15, with questions. Okay, we're going to prove real fast that the information doesn't exist until we measure it. Okay. So this was the basis for the Nobel Prize in Physics. This is the last set of things I want to do. So, interestingly, Einstein realized that quantum entanglement was super freaking weird. He defined something he called realism, the reality of a physical quantity, right? Which was that you should be able to predict it without disturbing the system, right? It shouldn't be the case that you can't, that your measurement is creating the information, as opposed to that your measurement is discovering the information. He objected to that. He understood that quantum mechanics predicted that, and he objected to it. He also very strongly objected to this instantaneous thing, right? This problem that you instantaneously know this thing in these separated places, right? But what he thought was that basically it had to mean that quantum mechanics was wrong, right? It was incomplete, right? It turns out that Einstein was wrong, interestingly. And in fact, quantum mechanics is, at least in this sense, complete. But his definition of realism doesn't hold. And his problem with this instantaneous making predictions across places is actually fine. Weird, but fine. And here's what we're gonna do. We're gonna go through this and then we're done. Okay. A guy named John Bell figured out 30 years after Einstein wrote that paper that these were mathematically inconsistent. It took another 10 years for anyone to figure out how to actually imagine making a physical measurement that showed that mathematical inconsistency, and another 10 years for anyone to actually make that measurement that showed the inconsistency. But now it's been 40 years, and people have been making this measurement routinely. I've got two polarization qubits. They're going off in different directions to Alice and Bob. Alice and Bob each have a polarizer, and they're randomly choosing to set it to two values, which we're labeling A1 and B1. Instead of 0 and 1 for my bits now, I'm going to use -1 and 1. It's because the math is a lot better. Obviously, if I told them 0 and 1, it wouldn't actually change anything. The math is just much more clear if I use -1 and 1. It doesn't matter how I label my bit. I could label it 7 and 13 if I wanted to, right? So this has to be a statistical measurement. So I'm going to create my two photons over and over and over and over again, right? And there are 4 possible measurements I can make because they're joint measurements. Alice and Bob could both pick 1. Alice could pick A2 and Bob could pick B2. Alice could pick A1 and Bob could pick B2. Alice could pick A2 and Bob could pick B1. Four things. These 4 things. We're going to measure each one of these 4 things many, 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 many times and take the average value. These brackets, these angle brackets here, those denote average. Right? That's all that means. It's the average value of the two. Obviously, if they get the same answer on both sides, the average, or the value of that particular pair is +1. It's either +1 times +1 or -1 times -1. If they get different outcomes, it's obviously -1, because 1 is +1. This is why the math is easier. The other is -1. So each one of these 4 average values is between + and -1. If it were just totally random, it'd be 0, because half the time they'd be the same and half the time they'd be different. Under normal classical physics realism, Einstein's favorite thing, right? A and B, the particles, they know what answer they would have given if I had made the other measurement, right? This is the assumption that measurement is the discovery of information that exists, not the creation of new information. So for every pair of particles, the particles still, even if I measured A1 over here, the particle kind of knows what it would have been if it was A2. I can at least mathematically write that number down as a number, right? Even though I can't actually access it or measure it. He actually called these are called hidden variables, because they're things that you can't actually measure, right? Fine, that means I can write this big sum with the minus sign on the last one of my 4 quantities. I can take my averages, my little carets, and put them on the outside, because for each pair, I get to consider the whole quantity. Even though I can't measure it, I'm only measuring the thing like this, but I can at least consider the total value of all 4 of these measurements for each pair. And I can take that average. And I can do the smallest, tiniest amount of math and rearrange that so that it looks like A1 times the sum of B1 and B2 plus A1 times the difference of B1 and B2. B1 and B2 are either the same or they're different. Those are the only options, right? If they're different, B1 plus B2 is 0. If they're the same, B1 minus B2 is 0. So for every pair, this thing is either 2 or -2. For every pair. The whole thing is either +2 or -2. So the average of a thing that's either +2 or -2 every time is between +2 and -2. Right? The only assumption I made was that I was allowed to consider all 4 measurements, or at least all 4 outcomes for each particle. Quantum mechanics doesn't ask you to make that assumption, right? Quantum mechanics says, no, 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 no. You don't get to think about the measurements you didn't make. You only get to think about the measurements that you made. These are not equal. You only get to think about the thing, which is the thing you're doing, which is the 4 separate measurements and their average values. And you get a prediction from quantum mechanics. If you start with our favorite entangled state, these are now polarization qubits, so instead of drawing them up, up, and down, down, I'm drawing them horizontal, horizontal, and vertical, vertical, right? if that's my entangled state, it turns out my measurement outcomes have to do with the difference between the angles. If the angles are the same, you always get the same outcome. If the angles are orthogonal, you always get opposite outcomes. Right? If they're somewhere in between, you have some probability. It turns out you don't have to know anything about trigonometry. It turns out that if you actually write them down mathematically, it ends up being the cosine of the angle between, of the twice the angle between the two polarizers. This is just the prediction that quantum mechanics makes, right? So the crazy thing is that that prediction can be as large as 2 times the square root of 2. So basically, as you vary the angles between these 4 polarizer settings, your quantum prediction is a curve that looks like this, that goes outside this range of 2 to minus 2, which we said the only assumption we made to get to to that range of 2 and minus 2 was that every pair of particles I make, I'm allowed to consider all 4 possible measurements for that pair of particles. That's the only assumption that I made. So, like I said, Einstein wrote his paper in 35, Bell wrote down his inequalities in 64. 4 guys wrote down a way to actually physically implement those. Bell's paper is very mathematical and impossible to read. 4 guys wrote down an actual physical way to measure those inequalities in 72. And then some more guys actually made the measurement in 82. It's now become routine to make a measurement. Right, how do we tell the difference between quantum physics and classical physics as we measure? It has now become a routine to make a measurement that strongly violates the limit in Bell's inequalities. This is data taken from the entangled photon source upstairs. These photons were not sent to the library. They were just, this data was taken within the lab upstairs, but this is the exact source they're going to use to send photons to the library this afternoon. And as they vary these polarizer angles, they see exactly what they expect, that they see this correlation cross the classical limit. Right. I think a lot of people, I wasn't around in 82, I think a lot of people were surprised at the time that quantum mechanics won. Right? I think there were probably a lot of people who expected that in fact it would be impossible to violate this limit and that classical physics would win. And the fact that it's real, that this has a real effect, that quantum entanglement has this real measurable effect on the universe is really what founded the whole idea of quantum computing and quantum information, which rely very heavily on entanglement. All right. I had extra slides in case somehow I went way faster than I meant to, which I will skip. So, currently people around the world, and a lot of people here at Illinois, are doing research on quantum networks. All sorts of different things. These are just different potential physical implementations of building a quantum network. I strongly encourage you all to come this afternoon. If you want to learn more, we have our Illinois Quantum Information Science and Technology Center that has a website. And I also encourage you, so the Quantum Atlas is a joint project between Illinois, the University of Illinois, and the University of Maryland. It's excellent. It's all correct, which is not true when you read the popular press about quantum mechanics. But the Quantum Atlas is entirely correct, and it's written at a level that is supposed to be accessible. And so I encourage you to take a look if you want to learn more. And thanks to my group and to everybody who funds my research.
Great. So we have time for questions from the audience.
Yeah, that 1935 Einstein paper said that the quantum mechanics was either wrong or incomplete.
Yep.
Maybe it was just a matter of being not complete at that time in terms of the understanding. What do you think?
I mean, he was arguing that quantum mechanics, as it's currently formulated, we haven't changed the formulation. Well, we have, but that's not what he was complaining about. Right? Quantum field theory didn't mostly exist at this time. He wasn't complaining about the things that quantum field theory fixed. Right? He was complaining about regular vanilla quantum mechanics, which is still the thing that we still understand, which is, so he doesn't say the word entanglement, he says non-commuting operators. It's the same effect, right? And he was complaining about the fact that by measuring one of these non-commuting operators, which in our case is like making some measurement here instead of making some other measurement, right? They couldn't have simultaneous reality. Where does it say it? Then either, or these two quantities cannot have simultaneous reality, right? Which is exactly that assumption. So my assumption that I wrote, that each pair of particles knows what answer they would give, that's the simultaneous reality of both possible measurements. That's exactly the thing he was complaining about. Yeah.
Why was the measured maximum Bell violation not the same as the theoretical maximum violation?
Okay, because Ujang, do you work on that source? No. Loss is probably the answer. So you can only, every measurement, so there's statistical uncertainty, which was that uncertainty we were talking about, but also even measurements, even within that, every measurement has some precision or some uncertainty on it or some error on it, right? And in this case, it's probably mostly loss. So some fraction of the photons that they make, in fact, a very large fraction of the photons that they make, they fail to measure, as it turns out, because you get optical losses everywhere. Yeah, Ujang.
I do know that their entanglement fidelity is not maximum.
So in fact, what's happening is the mechanism, the physical mechanism that they're using to make entanglement also requires them to precisely kind of align some things. And if their alignment is a little off, which it is, then they won't, the state that they're making won't actually be like this. It'll be a little bit away from that. And if your state is a little bit different from that, it's not perfectly both horizontal, both vertical, but it's okay, occasionally actually one's horizontal and one's vertical, then you also won't get that maximum violation.
Elizabeth, maybe can you expand on that a little bit? Because there's a common question about what makes two particles entangled
Okay.
and how you do that in a lab.
Yeah. So I have a picture of it on my last slide. So that pretty picture of the rings there, that's a real color picture of light coming out of what's called a nonlinear optical crystal. And the photons that you're seeing that are hitting the camera for that are actually entangled. So the primary way that we make entangled photons is we use some material that naturally has the property that it can take one photon, in this case that photon would have been at the ultraviolet wavelength to start, so they used an ultraviolet laser. It takes one photon at a UV color and very, very occasionally splits it in two. Now, the laws of the universe tell me that I must conserve energy and momentum, right? In addition to the laws of the universe telling me I cannot communicate superluminally or faster than the speed of light, they tell me I must conserve energy and momentum, which means that if I start with one blue or UV photon, I have to make two photons that are each lower energy. So the color of a photon is related to its energy. UV photons are higher energy, red photons are lower energy. So for every blue photon over here, there's a red photon over there that came out at the same time. They also have to come out in opposite directions because I have to conserve momentum, and it turns out light carries a little bit of momentum. So every time these two photons come out, they'll come out at kind of random colors and in random directions, but always correlated, perfectly correlated, in order to conserve energy and momentum, right? And then what I have to do to actually make entangled photons is I have to very carefully collect the exact matching spots, right? So that I'm not accidentally collecting some photons over here and I'm not collecting their partners over here, right? And that's why entanglement fidelity might not be perfect. That's why the source might not be making exactly the state that you want. Yeah. So there are a lot of commercial crystals you can buy that will do this when you shine a very intense laser at them. But it can be tricky to actually turn that into a real entangled photon source that's good. It's easy to make a bad entangled photon source, I suppose.
Assume we make more progress in our understanding of quantum computer quantum network. How does the world look like in 20, 30 years? What kind of things would you be able to do?
That's a great question. I'm going to be pessimistic and say in 20, 30 years, it's pretty similar to what it is now, especially for quantum networking. So quantum computing, you might have heard, right? There are companies that say that they have quantum computers now, and they're getting bigger and better every day. The quantum computers today There is still no quantum computer today that can do anything that anyone cares about any better than a classical computer can do. So quantum computers today have not yet met that threshold of usefulness. I think most people believe that as they continue to get better, they will meet that threshold of usefulness somewhere between 10 and 50 years from now. But I mean, I don't know when. It's kind of mostly engineering problems, very hard engineering problems, real research engineering problems. The fundamental physics we think we understand, but there's a possibility as we continue to make quantum computers bigger and bigger, something will occur that we don't understand, and we'll have to revise our understanding of the fundamental physics of these systems. Quantum networking, connecting together these quantum computers with light, is even harder than building the quantum computers themselves in a sense, and so it's probably a bit behind, and will remain a bit behind. But eventually a quantum network will allow the quantum computers to be more useful, because it's going to be hard to build one quantum computer that's very big, but we'll be able to network them together to bootstrap them. It will allow things like you, the user, to use IBM's quantum computer without having to tell IBM what you want to do on it, which is going to be very important. If only a few entities have quantum computers, we want to make sure that they're accessible without you having to tell that entity what it is that you're doing, right? If it's proprietary or whatever, you don't want to tell IBM what computation you're making necessarily. So quantum networks will allow that, right? They will also allow certain kind of security things in communication. In theory, this is very, very, very far away because things that we would have to do to make this work. But in theory, you could build a voting system where no one has to trust anyone. So you could actually build a system where everybody sends a qubit, which is their vote, and then they all come to a common place, but the person at the common place can't change anybody's vote because of the way that the measurement changes things. And everyone can verify that their vote was counted correctly via these kind of entanglement measures, right? Don't ask me how that works. I could direct you to the correct person here at the university who thinks about those kinds of things, these kind of quantum security protocols, information security protocols with quantum, but there are a bunch of those as well. And then sensing, right? If you can network together telescopes or clocks or satellites or anything like this, you can get much, much more precise imaging of things, even at very long distances, right? Or looking from satellites to Earth. And that could also be very useful for a lot of things.
The back. Oh, you go first, then you go next.
Last week, we heard about the gyromagnetic constant of muon.
Okay.
And one of the challenges to measure that is that there is likelihood of virtual particles affecting that transition. Is there any virtual particle effect on the entanglement of photons?
The short answer is no. Obviously, physics is physics, right? The virtual, so Aida gave last week's?
It was David Herzog.
Okay. Obviously, physics is physics, so virtual particles are certainly always present. They don't matter for our purposes for a long list of reasons. So one of which is that our temperatures are very low, and we're looking at low energies and not high energies. So measuring G-2 is at a particle collider. They're at the absolute opposite end of the energy scale that we're at, right? So they have just a totally different set of problems than we have, right? They're making things at very, very high energies. There is a sense in which, I'm trying to think of virtual, we have to account for the virtual particles, and all they do is well, I don't. Somebody already accounted for the virtual particles, and I get to look this up. They change certain physical parameters in my system, but I don't care. I only need to know what those parameters are. I don't need to know why they are what they are as a general rule.
If the values depend on measurement, are there any complications when two entangled particles are measured at exactly the same time?
It's really a good question. So because the measurements are correlated instantaneously, basically no. They're also, when things are separated exactly the same time, isn't very well defined, right? But because there's no communication happening between them, and because there is this instantaneous correlation, that's why it's fine. That's kind of the thing that Einstein was objecting to. He was making this point that it shouldn't be, it should matter, right, if they were measured instantaneously with no time separation. But it doesn't. Yeah. It's weird.
More questions from the audience. In the back.
Yes. Are you transmitting between the library and here via
Great,
electric lines?
great question. I didn't say anything about that. Thank you. By optical fiber. So I have a demo on this, which may or may not work. Let me see. So that doesn't work very well. So optical fiber is just a very skinny piece of glass that when you send light down it, the light gets guided through the optical fiber. This is a piece of lucite, basically. And if I send my laser in there, can you kind of see that I'm making a spot on there, right? It's guiding my light, right? So this is like a fake optical fiber. So optical fiber is used to transmit classical signals all over the place. Many of you probably have fiber internet at home, right? That's light pulses coming down that are transmitting your bits, right? That are encoding your bits. We're going to send single photons down that optical fiber. Problem is most of them are going to get lost. And they'll be, but they can still be transmitted just the same down the optical fiber. It's hard to send things through free space over any distance because air currents, actually, and so you get things happening. You can send things up to satellites. It also comes with a lot of loss because of the air in the atmosphere. Yeah.
So where does the cable run?
I mean, underground.
Underground?
Yeah, I mean, that's where most optical fibers are underground. So some are probably strung from.
I mean, this wasn't a pre-existing fiber cable?
It is, actually. There's a whole fiber network in Champaign-Urbana that connects together most public buildings, as it turns out. UC2B. So it was an attempt to try and connect together, community schools. So most of the schools in the area are on this network. The libraries, the university, also lots of people's houses. I looked at the map to try and see if my house was on it. It definitely runs under my house. I don't know if we're actually connected to it. But so we're starting with the library, but we're going to expand this to schools and things. So we would like to start adding more and more things to this quantum network and connect it up to schools, use it as a teaching tool. Yeah.
But the source of entangled photons will be here.
The source will be here.
Yeah.
The photons are going to go to the library. You're going to be able to make that measurement choice at the library with a polarizer there, but then the photons actually come back here to get measured. Because it turns out the measuring single photons is not so easy. Yeah. We could, in theory, move the measurement device there, but it's easier to just send them back.
Sure. I think I saw someone raise their hand over there. Am I right? No? Okay. Any more questions?
Is that, yeah?
I'm just curious what protocol we use to send the data to the destination if we're going through the...
Yeah, so, right, you sound like a real networking person. And you say the word protocol. And yeah, right, our data rate is going to be some photons per second, right? We are literally just going to send single photons encoded with the quantum bit encoded in their polarization down and back. There is, of course, also classical communication that has to go on overlaid with the quantum communication. I do not know what the protocol is going to be for that. That might have a real protocol attached to it. Yeah. Do you know? Do you know what protocol, classical communication protocol they use? No.
We can find out.
Right. So yeah, oh, good point. If you come this afternoon, someone there's going to know. Thank you.
When you have your classical communication, you usually use an algorithm for security. Do you need some kind of an algorithm for this theory?
Yeah, great question. So when you do classical communication, typically today the algorithms that you use for security are things like RSA and public key encryption, which are not secure against a future quantum computer, which is one problem with them. There are classical algorithms that are secure against future quantum computing. Confusingly, this field is called post-quantum cryptography, which is people who are developing algorithms that are secure against future quantum computers. Classical algorithms that are secure against future quantum computers. Quantum secure communication comes from the fact that if you measure a quantum bit, you change it. And you can't copy it. And if you add those two things together, that gives you perfect security, in a sense. Right? So the main point-to-point secure way to communicate quantum mechanically is called quantum key distribution. It's basically, I use all of the things that I just described to simultaneously create the same random bit string in two places in a way that no one could have intercepted. Because it doesn't transmit, right? The information doesn't exist until I measure it, which means I didn't transmit this bit string from one place to another. It simultaneously appeared in two places when I did that Bell measurement, right? And now both people have this random bit string. They just encrypt one-time pad encryption, which is always perfectly secure if your one-time pad is secure. They just, as long as the random bit string is as long as their message, they can encrypt perfectly, and then they can decrypt.
Okay, last question.
You said that the measurement is actually happening here because we're
Yes.
sending photons back here.
Isn't that true?
So I guess my question is, I think they actually project onto the states there.
Yeah.
So once you do the projection,
Yeah, where's the measurement happening? This is a
where's-
philosophical question. You're right, you're right. The measurement choice is being made there.
yeah,
Then the actual measurement is happening here.
I guess the detection is happening,
The detection is happening here.
but then
But the measurement choice is being made there.
since
The
you started
polarizer,
off by saying that once you make the measurement choice, you basically will
you're right, you're right. It's fair, it's totally fair. Right, if I go back to my picture here, this is at the this is here, this is at the library, and then this is here again. Yeah.
Okay, wonderful. Let's thank Elizabeth again for a great, fascinating talk.